Potato is mainly used to elevate ordinary user or service user with impersonation privilege or assign permeate. Token privileges to system privileges. Usually, web server and database service have these privileges. In writing operations, our entrance usually comes from the web server. After obtaining the web after server privileges, we may just have a shell with normal user. Through Potato, you can elevate your privileges to system. It is worth nothing that Potato used for privilege escalation will not be considered a vulnerability by Microsoft, so potatoes will not be repaired. Brain machine found the first potato, which is based on WPAD cache, poisoning, and NTLM relay. It first impersonates the NBNS protocol, impersonates the WAPD domain name, and resolves the WPAD domain name system to the IPv control. When the system requests WAPD configuration, we will receive a request from the system. We can send a 301 response to the system. Let the Windows system provide NTLM authentication and authenticate the WAPD NTLM to the SMB service to obtain the highest permission of system. This is one of the methods used by potatoes, named PEP simulation. We need to allow high-privileged accounts to access our customer PEPs. After they access our PEPs and write, we can simulate the client of the PEP. In the first step, we use a low-privilege account to create a named PEP and set the permissions of the PEP so that anyone has access. The second step is to allow high-privileged user to connect to the named PEP we create, such as EFS RPC open field role, RPC remote find first printer change notification extension in RPC. In the third step, a high-privileged user connects to our named PEP. The fourth step is to call impersonate name PEP client API to simulate the authority of the client, and call open thread token to obtain the simulate token. The first step is to use a high-privilege account to create a process to achieve privilege escalation. This is one of the methods used by Potato. DCOM simulate we need to let the account with high authority call our custom COM mass. When calling our custom COM mass, we can simulate the user. It is worth nothing that DCOM objects can call each other. There is no distinction between server and client. In the first step, we used a low-privilege account to create a fake storage object or fake unknown. The second step is to call the go-get instance from iStorage mass to allow high-privileged user to deserialize our COM objects. In the third step, the release mass of fake stored will be called by a high-privileged user at this time. The fourth step is to call CO impersonate client API to simulate the authority of the caller, and call open thread token to obtain the simulate token. The fifth step is to use a high-privilege account to create a process to achieve privilege escalation. This is one of the methods used by Potato. RPC simulation, we need to let high-privilege account call our evil RPC service. We can use the debugging tool to find some mass that the system is trying to call, but the RPC has not been created. In the first step, we use a low-privilege account to create a fake RPC server. The second step is to wait for the high-privileged user to call our evil RPC service. In the third step, high-privileged user call our RPC mask. The first step is to call RPC impersonate client API to simulate the authority of the caller, and call open thread token to obtain the simulated token. The fifth step is to use a high privilege account to create a process to achieve privilege escalation. This is the way of using potatoes NTM relay. We need to allow high privilege user to authenticate us. For example, GodPotato does this. This first step is to use a low privilege account to create a relay service. The authentication based on the TCP protocol is commonly used in Potato, but HTTP authentication is also available. The second step is to let high privilege user initiate authentication to us in some way. For example, GodPotato is the authentication obtained in Resolve OXID 2. In the third step, user will have authority come to authenticate us. The fourth step is to call the accept security context mask to relay. In the fifth and sixth steps, use the query security context token mask to obtain the token of the context. The seventh step is to use a high privilege account to create a process to achieve privilege escalation. COM is an object-oriented programming model, which has nothing to do with programming languages. DCOM is a remote call version of COM. DCOM supports communication calls between different processes, different machines, and even different operating systems. It can be said that DCOM is a part of RPC. When making an ORPC call, if the passed parameters is a reference object, the caller will serialize the object into a M interface pointer structure, which will be deserialized by the call. The serialized data will be stored in the M interface pointer structure, where the AB data field of the M interface pointer structure is the content of the OBJREF structure, and URL CNT data in the length of the OBJREF structure. The more important thing in OBJREF standard is SARES address, which indicates the network address where the DCOM object should be searched. Port 1035 of this address in an RPC service, and there is an OXID resolver in it. When the DCOM object is deserialized, it will guide RPCs to call resolver OXID to find the real IP and part of the object. As shown in the figure, OXID is the target to be searched, and the PLT sequence is the communication protocol of the expected DCOM object. OXID returns the address where the DCOM object is located. We see that it returns a random high port string. Our application does not listen to this port. Why is it listening on this port? Who is it listening to, RPCSS or myself? Through the process hacker tool, we found that we are listening to the high port 51386. We need to filter debug and find out. After the breakpoint in the listen mask of the WS232 model, the following call stack was found. From the call stack, it is obvious that other programs called us through RPC. We seem to have entered a rabbit hole. Through the RPC tool, we can clearly see that It has registered an RPC, which has 5 public masks, but we have not registered this RPC interface. After searching the UID of the RPC interface through Google, we got such an IDL. It is not difficult to find out through the comment information of the IDL. That is, one is provide to the object resolver to register a specific RPC protocol series. After thinking about it, it is not difficult to find that when we initiate resolve oxid2 to the RPCSS process during operation, RPCSS will call the RPC mask of use protocol sequence of our process, where the W toward ID parameter is the RPC protocol to be registered. When we query RPCSS for oxid, RPCSS will call our process to let us bind the specific RPC protocol and return the bound RPC address and pause as PPD's new bindings parameters to RPCSS. Will RPCSS check the value of this parameter? Can we fake it? After modifying the return value through debug, the conclusion is correct. Yes, RPCSS fully agrees with our modified value. We successfully changed the value to HITB and PhD days, which means that now we can custom the RPC communication address of the DCOM object. Now we can custom the oxid bindings. Now we can accept calls from RPCSS in order to make use of it. Let's take a look at the protocol supported by Windows RPC. So as a escalation subsequent exploitation from the table, we can see which protocol Windows RPCS supports, such as the commonly used NCAC protocol or NP protocol. From the potato and utilization process we discussed earlier, we now have 2 utilization masks. One is to implement the RPC protocol ourselves for simulation, and the other is to use named PAPs for simulation. In order to facilitate our use of named PAPs, COM is an object-oriented programming model which has nothing to do with programming languages. DCOM is a remote call version of COM. DCOM supports communication calls between different processes, different machines, and even different operating systems. It can be said that DCOM is kind of RPC. So the exploit steps are as follows. Step 1, find RPC ORCB stop because we want to hook its use protocol sequence function. Start the eval-pap service. Step 3, use protocol sequence function of hook ORCB. Step 4, trigger resolve OXID. Step 5, wait for RPCSS to initiate a user protocol sequence call to us. Step 6, once RPCSS is invoked, we send the eval RPC named pipe address. Step 7, wait for RPCSS to contend to our eval named pipe. Step 8, once RPCSS connections our eval pipe, we call impersonate named pipe client to impersonate it. Step 9 and 10, obtain the token of the high privilege account and create a process. After understanding the idea of the vulnerability, we began to write the exploit code. First, we obtained all the loaded DAOs and searched for a model named combase.dao. and then search for the RPC sub future of ORCB at the memory address of com-base.dom. Once found ORCB step, we will pass it and get the function address of use protocol sequence. After that, we can create our evil named pub and set the permission of the named pub to be accessible by anyone. Once that named pub is connected, we will simulate the named pub client and get its token. The use protocol sequence mask after writing the hook returns the URPC named pub address. Since the number of the parameters of each version of the ORCB RPC service is different, we need to manipulate masks with different parameters and dynamically obtain the delayed instance through reflection, and then obtain the memory address of the delayed through module and write it to ORCB dispatcher table. After running, we have obtained two user privileges of network service. Why is it not a system? We found that RPCSS itself had a network service permission rather than a system. However, there is a token and bingo with system permission in the handle of the RPCSS process. Now, all we need to do is to traverse the handle of the RPCSS process and steal the handle of the system after obtaining the work service permission. This is a screenshot of successful exploited. Now the new user is system. Okay, it's finished. The project has been released to GitHub. Okay, it's finished. Thank you.